Okay, let's get the show rolling. I'm Simon again. I was here yesterday. It's my pleasure to introduce this morning my colleagues from Yale. And first up is Professor Corey O'Hearn, who's going to talk about dense random packing in protein cores.
Is my mic on? Can you hear me?
Yeah.
So first, let's introduce the actors here. So Lynn Regan is a longtime colleague, and we have several co-advised graduate students that have been working on proteins at Yale. The main players for this talk are Jennifer Gaines and Wendell Smith, but we also mentor these other two students. The funding for this work has been provided by the RBSI Institute at Yale, NIH training grant, and iPoLS. So today we're going to focus on protein structure. And what I mean by that is the conformations of the side chains, what selects the side chain dihedral angles, and about the packing fraction, how densely packed is the core. And we believe that a fundamental understanding of these quantities is important for understanding structure-function relationships in proteins and determining controlling protein-protein interactions. Because it's early in the morning today, we're going to try to overturn two paradigms in protein science. The first one is contained in this paragraph that's quoted from a Dill paper in 2001, and it's about packing in protein cores. So I'll just read it. What is a good model for the packing inside a protein? Is the protein packed more like a liquid or a solid? Based on the observation of high packing densities by Fred Richards, who was a longtime Yale professor, and low compressibilities, protein cores are often considered to be more solid-like than liquid. Packing in proteins was first analyzed quantitatively by Richards and by John Finney. They used a Voronoi analysis of proteins in a space-filling model where each atom is taken to be a sphere with a fixed radius given by the van Waals radius. These and other classic papers show that the average packing density in a protein is as high as that inside crystalline solids. And this has been taken to be basically dogma since the early 70s. And I want to challenge this paradigm. The second paradigm that I want to challenge is the idea that complex or well-developed force fields need to be used. Those that are used in for example, Amber and Charm software need to be used to quantitatively understand the structure of proteins. And so I want to argue today that the answer to this question is yes, can the structural properties quantitatively understood using hardware models. So here's a figure taken from one of the seminal papers on protein packing. It shows the packing density, and we're going to talk about this extensively about how this is defined. The packing fraction, which I will use to denote as phi, is the volume of the core residues in the interior of proteins divided by the volume that contains those residues. And so what they're showing, Dill is showing in this paper is the packing density as a function of the number of residues in proteins. And so there's some very high packing densities for small proteins, but then they even out approaching 70 to 74% for large proteins. And the issue that they were raising in this paper is that's pretty high. In fact, if you have monodispersed spheres, the densest packing, which was just recently proven, is 74%. That's the highest density you can get for monodispersed spheres, and they occur in an FCC lattice, a base-centered cubic lattice. And so this was determined as the result. And so I want to first just talk intuitively or schematically about that result, that protein cores really packed at 70 to 74%. Is that actually tenable? And the first thing I want to do is remind you about how monodispersed spheres pack. What I'm showing here is an order parameter. This is the translational order parameter, bond orientation order parameter Q6. Basically tells you how how much FCC order there is. And you can see I've shown pictures that show you this is low Q6 order, it's random packing, and then FCC is ordered up at 74%. And what it shows is that for sphere packings, these monodispersed sphere packings, there's a density or increased packing fraction coincides with increased order. So at 64%, which is a relatively low packing fraction, you're going to be disordered. But as you increase the packing fraction, you necessarily have to increase the order in your system. And so, well, if you're going to say something's packed at 74%, you better believe that there's some order in the system. Now, what we normally say is, well, protein amino acids are not monodispersed spheres. So let's investigate that issue. So the first thing is to get you to start thinking about what happens to packings when you don't study spheres. And so what I'm going to show you here schematically is you have to think about the following. Here on the vertical axis is a generic non-sphericity parameter, which could be elongation. So for example, if you're studying ellipses, it could be the aspect ratio of the ellipse. Here's a schematic of what happens with spheres. There's random closed packing that occurs at 64%, and then there's a crystalline value that happens for FCC. But then you can imagine doing this for every shape, and here's my schematic for doing that. Again, if you study a different shape, say something that's slightly elongated, you're going to get an RCP value and you're going to get a crystalline value. Then you have to think about how are those going to vary as you change the shape of your object, because amino acids are not spherical. And here's what it does. I've done this, and others have done this, for different particles that just have one, basically, parameter, an elongation parameter. We studied spherocylinders, where you can increase the length of the particle. We studied ellipsoids, we changed the aspect ratio. We studied dimers, two spheres joined together. And generically, this is what happens. There's a small range, so at aspect ratio of 1, you get spheres. They pack randomly at 64%. And the random closed packing value has a small increase for low aspect ratios, and then decreases strongly at large aspect ratios. Now this is for objects that have basically one feature. They become elongated. We're going to show later that systems that are rough and don't have just one elongation parameter, this actually just goes down as you increase the non-sphericity. Okay, so for the physicists in the audience, here's the cornucopia of amino acids. And what I want to get at this plot is these are stick representations of 11 of the 20 flavors of amino acids. What I want to show you is that what's common to all amino acids is a backbone, which has nitrogen, carbon, and carboxyl groups, carbon and associated oxygen. And those are the same across all amino acids. All amino acids have the same backbone. What differentiates one amino acid from another is the side chain that sticks off. So for alanine, it's short and not very complicated. But for tyrosine, methionine, they're larger, and they are characterized by more degrees of freedom. In this case, the side chain dihedral angles, and we're going to talk about that in a second. So Jennifer talked a little bit about this yesterday, but we are very closely tied, our models are very closely tied to experimental observations, that is, protein crystal structures. The database that we chose to compare to is a Dungraph database of high-resolution protein crystal structures, resolutions of 1 angstrom or less. And here I'm just showing you that it's a large data set. There are more than 1,000, typically 2,000 or 3,000 instances of each residue, and so we have a large sample to compare. What's nice about that database is we can basically fix some structural properties of the system in our model. That is, for example, here I'm showing you an alanine dipeptide, and it has stereochemistry that's fixed. For example, the bond angles, which are given by every 3 atoms who have a bond angle, it needs to be along the backbone or along the side chain. Those we're going to think of as fixed and given by the protein database. And here are those distributions. They're fairly tight, 5 or 10 degrees width. And then the bond lengths, which are determined by every 2 bonded atoms, they have very tight distributions. And we get those from the database. The next thing that we can think about are backbone dihedral angles, which characterize amino acids. They are phi and psi, and they're determined by 4 bonded atoms. So here I'm showing you just a chain of 4 bonded atoms, I-2 through I+1, and a dihedral angle. So if we say we have n atoms and we take away the bond length constraints and the bond angle constraints, that leaves us n-3 degrees of freedom, and these are termed as the dihedral angles. In this case, 3 atoms, I-2, I-1, and I form a plane. There's a normal to that plane, which I'm just labeling as pi1. And then there's 3 other atoms, I-1, I, and I+1. That defines a plane. And the dot product between the normals of those planes defines a dihedral angle. You can have backbone dihedral angles, and you can have side chain dihedral angles. I'm going to talk about that in 1 second. One thing that I want to get across, which Jennifer talked about yesterday, is that you can have constraints or clashes between atoms within a dipeptide, and you can have clashes that are from one amino acid to another. We're going to think of as the 0th approximation of just clashes within the dipeptide. And then as an improvement of our model, we can think about what happens from one clashes between one residue and another. So here is the classical Ramachandran plot. And back in 1965, Ramachandran, what he did is he looked at an alanine dipeptide. He specified atom sizes for all the atoms in the alanine dipeptide. And then he said, what are the configurations, the backbone, the dihedral angle configurations that are sterically allowed, that wouldn't cause clashes between the atoms that he specified in the alanine dipeptide? Those conformations are delimited by these solid lines. So for simplicity, let's just look at the pink lines. He says the sterically allowed configurations have to live within the pink lines. And he looked at the crystal structures of that day, and they fell within those pink lines. What I'm showing you now is the latest incarnation of the Dunbrack database, all structures in the database, and I'm plotting the phi psi values. And you see that to basically 99%, the crystal structures fall within the Ramachandran hard sphere limits. So hard sphere models do a good job of modeling the backbone dihedral angles. Now you should all look up at this point. This is the first paradigm that I'm challenging. Here I'm showing amber, and here I'm showing charm, the latest charm force field, charm 27, without an associated water model, simulations of alanine dipeptide, but I'm not including the knowledge-based terms, the knowledge-based corrections. I'm showing the same plot I showed before, the Dunbrack database of protein crystal structures fall within that, and so a force field should recapitulate that. And here, the charmed force field without knowledge-based corrections has an issue, does well in alpha and beta. It has this issue at psi values between -60 and 180. There is populating structures that are sterically disallowed. Okay, so I talked about phi psi values of backbone dihedral angles, and now I'm going to talk about side chains. Because these side chains, what's different about what we're doing now and what was done in the past for packing proteins is we're going to try to determine atomic radiuses, radii that make sense. And so the way we're going to do that is we're going to look at the side chain dihedral angle distributions and try to recover them. And we're going to focus on the residues leucine, valine, and isoleucine. Okay, so here's a generalization of what Jennifer talked about yesterday with our method. What I'm showing you here is an interatomic potential between non-bonded atoms That's the repulsive Leonard-Jones potential. You see that it's a non-zero value when atoms overlap each other, that is when the separation is less than the sum of their diameters, and it's 0 if they don't overlap each other. And what we're going to do is calculate Boltzmann weights of the total potential energy that's summed over all the atoms, all the pair interactions in a residue, and then we're going to exponentiate that. And what Jennifer talked to you about yesterday was the hard sphere limit, and you can take the hard sphere limit by taking the temperature to 0. That makes these exponentials all very large if there's a finite value of the potential energy. So a picture is worth 1,000 words, and so here's literally what we do in a movie. So here I have a leucine amino acid that's taken directly from the Dunbar database. It has fixed values of phi and psi, fixed values of bond length and bond angle, and a fixed chi1. And what we're going to do is rotate around chi2, and I'm going to plot the Leonard-Jones, repulsed Leonard-Jones potential energy. The vertical dashed line is the crystal structure value. And this is what we do with our calculations. We basically calculate all the pair interactions between non-bonded atoms. We calculate the total potential energy. And you see that because there are clashes between the atoms, if you saw that movie, the clashes will appear in orange, which matches the color of the potential energy plot. You're supposed to go, wow, that's fancy. And the nice thing about this is that the crystal structure corresponds to a zero energy of the potential energy. And so we do that for all leucines in the Dunbar database and calculate the probabilities to have a certain value of chi1 and chi2 for leucine. Okay, so now we're going to start talking about packing with cores. And so the first thing you have to do is decide what a core residue is. And there are many ways to do this. We've done it many ways, and you have to make sure that these ways agree. Here I'm just going to show you one way, just for illustration purposes. We take a protein, there's a protein in there, and we put it in a box, just to confine it. And then we throw down points randomly. We throw down billions and millions of points. And what we do is we look at a point and we say, how far is it from the nearest atom? If it's farther than the distance, the size of a water molecule to the closest atom, we say it's a surface residue. Okay? And that's how we identify, we do that millions and millions of times, and that's how we identify the surface residue. There's also a subtle issue about voids. We also can identify voids. There could be a void inside this, and the same thing holds. We see if the nearest residue to that point is bigger than a water molecule away, we determine it as a void or as a surface residue. Here are our results. They're not surprising. These are we looked at all the proteins in the Dunbar database, and we find the percentage in the core and the percentage on the surface. Separately, the percentage in the core sums to 100%, and separately, the percentage on the surface sums to 100%. And we define the core residues as though that the percentage of the core is greater than the percentage on the surface. So the core residues are leucine, alanine, valine, isoleucine, glycine, phenylalanine, cysteine, and methionine. We're going to focus on the top 4 or 5. Okay? So the next thing that we have our core residues, the next thing we have to do in our model is believe in our atomic radii. What we choose for our atomic radii seems arbitrary. So what we're going to do is we're going to choose atomic radii that give us back side chain dihedral angle distributions. Here are the observed side chain dihedral angle distributions from the Dunbar database. Jennifer showed these yesterday. These are the ones that just have one dihedral angle. This is valine. It has a high probability rotamer at 180 degrees. Here is cysteine. It has a high probability rotamer at 300 degrees. Here's leucine and isoleucine. Leucine and isoleucine have 2 dihedral angles, chi1 and chi2, and they are notorious for having these 2 high probability peaks, and isoleucine has this one. And we want to have atomic radii in a model that recapitulates this data. Jennifer talked to you about that. She has a poster of how she did that. Here are the results. So we looked at the literature. We found van der Waals radii for all the atoms in the residues, and here they're listed. And we can play this game where you could have a radius for every pair atom. And you can break it up into 24 atoms types. She talked about 12 yesterday. But the nice thing about that is you can do the largest breakdown, but then you want to see if you get any commonality when you do those studies. So what we're trying to do is determine the atomic radii that best match the side chain dihedral distributions. Our results are the black circles, and all the previous data are all the other symbols. And so we have hydrogen atom types here, we have carbon atom types here, and oxygen and sulfur. So what you want to see is, by and large, our atomic radii are basically falling within the atomic radii that have been studied before. We don't have to do anything crazy to match the side chain dihedral distribution of certain proteins. A lot of them are sort of typical. Maybe if you want to see anything from our studies, maybe the nitrogen is a little smaller than what's been found before, or what's been used before. And so Jennifer showed this. We get pretty good agreement between the observed and the calculated distributions daily. We recover 3 rotamers, and the highest probability rotamer is 180. Same for cysteine. We recovered 3 rotamer peaks, and the highest value is 300. Here we also show leucine and isoleucine, which now have 2 values of chi1, 2 side chain dihedral angles, chi1 and chi2, and we do pretty well. One thing that I would point out is that this rotamer is slightly less populated, and so is this one. But we also have another trick under our sleeve that this is just for the dipeptide. These residues live in the protein environment, and so we've shown that when you include the local environment, these dihedral angle maps improve and actually get quantitatively correct. Okay, so now we have a model, and I would argue, listen to this, that this is currently the best atomic model for our protein structure. Of course, we'll go to that. Because it maps, it can specifically recover the side chain dihedral distributions without long-phase potentials. So now we have this model. Now we're going to go back and study the packing of protein cores because we have this great atomic level model. The key thing for calculating packing fractions is to define volume. You have to take the ratio of 2 volumes. The numerator is going to be the volume so here I'm talking about packing fraction per residue. If you sum up all the residues in the core, you get the packing fraction of the protein core. So you have to define the volume that the residue takes up, and you have to define the container that the residue sits in. So here, the volume of the residue is simple. Here we have our atomistic level reconstruction of all the residues. We use that to calculate the side chain dihedral angle distributions. Here they are in their full glory with explicit hydrogen. You can actually calculate the exact volume of these structures. Here they are in extremes cubed. So that's the numerator. The numerator is simple. The denominators is a little more subject to choice, especially if you have voids and surfaces, but I got rid of that, and I'm going to use the Voronoi tessellation to define the volume that contains the atoms in the residue. So Voronoi tessellation quickly is just an object that contains points that are closer to this particular atom than any other atom. And so here is the Voronoi polyhedra that correspond to a leucine residue. And so the packing fraction of this atom will be the volume of that atom divided by the volume of the polyhedra that contains that, and then you can do the same for the entire residue. Here are the values. You want to focus on the left because those are the residues that are prevalent in the core. And here we see the packing fraction of the residues. You want to pay most attention to leucine, valine, and isoleucine because those were the most prevalent in the cores. They have packing fractions in the mid-50s, and the other residues have packing fractions in the mid-60s. So you're already seeing an issue here. So here I show you the actual protein by protein. This is a distribution of the packing fraction of the protein cores for all proteins in the Dunbrack database. That's this blue line. It has a strong peak of 55%, not 70%, not 74%. Here's the data from our method of the databases used in the previous work, and the key point is that they use extended atom instead of explicit hydrogens. You notice that those peaks are higher, around 67%. They're not at 70 or 72% because we used a slightly different definition of the bounding container. Here you can sort of see why we get different results. Here's the previous model that the folks used for packing in the core. They used extended atoms for the carbons and to model the hydrogens. And so those are bigger structures, take up more of the volume. Whereas here we use explicit hydrogens and atomic radii that we believe makes sense. Okay, here, if you haven't been blown away, this should blow you away. This is now, we're going to go back around and try to reconstruct protein packings from a simple-minded simulation. What I'm going to do is throw residues in a box that match the concentration in protein cores, and then just compress them and see what packing fraction I get. So you throw residues in a box, compress them, what packing fraction do you think you get? You get the one that we saw in protein cores. So here I'm going to play the movie for you. It's just a small system to just show you what happens. So these are all leucine. What we do is these leucine residues interact with purely repulsive interactions. We compress the container until the systems jam and form this jam structure. And what I'm going to show you here is the same plot that I showed before, the previous results that occur at upwards of 67 to 70%. I show you the Dunbrack database results and the blue peak distribution, and then I carry out the simulation, these simple-minded simulations of just packing residues in a box. I do that millions of times or thousands of times. I haven't done them millions of times yet. And I show the distribution of what I get. And you see that they're showing peaks near 55 in the mid to lower 50s. Okay, so what we've done here, I will conclude now. Tell you what we've done. The previous calculations of packing fraction of the core seem high to me now. 70 to 74%, near packing fractions of crystalline solids. It's likely too high for protein core packing. Just intuitively, this seems to me like it would imply positional order and very, 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 very rigid structures. We predict instead that the packing fraction of protein cores is in the mid-50s. We used a Hartsford model with explicit hydrogen and atomic radii that makes sense, and that i.e. they were mapped to observe scientific hydrogen distributions. This is enormous, so I'm either crazy, wrong, or right. A 20% discrepancy in packing fraction is enormous because typically these packing fractions are exponentiated in models. The other thing that I think is very interesting is that the packing fraction of the core can be obtained from a very simple simulation, just throwing residues in a box and compressing them. I get 56%, which matches the results from the protein database. What we want to do now is apply these results to repacking the protein cores. We need targets. So for example, if you're trying to repack something, if you're trying to design a protein-protein interface, you need a target. You're getting a very different answer if your target packing fraction is 70%, whereas compared to your target packing fraction is in the mid-50s. And with that, I will conclude.
Any questions for Corey?
So you've totally ignored van der Waals interactions, positive, attractive interactions, but although that would be easy to include when you do your energy scheme. So have you considered that?
Yes, so we truncated the Leonard-Jones interaction, right at the repulsive part. We didn't include attractive interactions. there are sort of two levels to that, two answers to that question. One is we want a very simple model that just includes repulsive interactions as a first level. And what I haven't told you is the second part of the story is that there are some residues which that doesn't work that well. The issue is with methionine. Methionine, thank goodness, is not that well populated in protein cores, so I didn't have to talk about it. But when you do methionine, especially with Chi3, the third dihedral angle, we get a very flat distribution. It doesn't really, the hard sphere model doesn't really pick out particular monomers. But we're thinking that van der Waals attractions may play a role. But the key thing that we want to do is that we want to now put in attractive interactions to all this and show that attractive interactions are subdominant compared to the hard sphere interactions.
Okay, that's nice, but there are lots of approximations on your models. So, for example, what's the radius on? First of all, you said I believe in hard spheres. You can have a long conversation. It should be hard spheres to start with. But also, you said I'm using the dihedral angle to get the absolutely correct hard sphere. If I get Sam here, she may tell you that's not the best number to fit the numbers. So I think there's a loop.
Well, I would like to have that conversation. So I think that for determining, if you want to do protein design, looking at the dihedral angles is a very good thing to do because,
no, I understand.
So then,
but you have to know it's a model. It's not the absolute truth. That may be good for one thing, but now you're telling me that gives you a radius, and that's the radius I should believe when I get packing. So is that enough? In a sense that that's much better than all the other radius that people chose for other properties when they fit. It was not my own.
So let me come back. So first thing is that intuitively, 70%, 74% is too high. I made intuitive arguments that said that that's way too high. So that's the first point.
No.
The second point is now I believe that's too high. So now I'm going to come up with a model that tries to explain that intuition. Our belief is that side chain dihedral angles control lots of.
So you said 75% is too high. I say 55% is too low. So, for example.
No, I have strong intuitive arguments in which you should address that show that 70% is too high.
So let me tell you another thing. A lot of the times when you do your packing, a lot of those voids in real proteins will be full by water. Basically, you're not going to have packs basically. I would like to see when you show me your final result, which cavities you left over, which space is not there. Is that just, okay? So I think there are other questions that need to be addressed. I agree with you, maybe 75% is too high. But I think that there are other things that you didn't include. What happens with places where water can be there?
Can you be explicit about the things that I didn't include? We talked about attractive interactions, and I have a reasonable argument against that. So I said that hard spheres recapitulate the dihedral angle distribution.
You just stated that it's not dominant. You didn't show us it's not dominant. That's what you wanted to. I mean.
No. I have 30 minutes, and I showed you what I had. So now what we're doing is there's one amino acid, methionine, that you can't model with just hard spheres. What we've done, and I can show you, we add attractive interactions, you get the same distributions.
So,
if you don't believe me, do it.
So, time is pressing, so maybe we can continue these conversations.